Matter can exist in a lot of different states. The most common of these are solids, liquids, and gases. But what makes a liquid, and what makes a gas? A lot of people have this picture, especially from science classes, that it's all about the motion of the molecules. The faster they're moving, the more likely it is to be a liquid and then a gas. But kinetic energy is not the only type of energy. There are more than 4 types of state changes, and no matter how long you boil a pot of water, the temperature is not going to go up. Welcome to Flip Physics. Today I'm going to talk about state changes, otherwise known as phase changes. Solids, liquids and gases. You warm up ice and it melts to form liquid water. You heat up the water and eventually boils to form steam or water vapor. You cool it down again and it condenses back into liquid water, and you cool it down even more and it freezes back into ice. So it's all about temperature, right? Wrong. Temperature is involved, sure enough, but it's only part of the picture. All particles have both kinetic energy and potential energy. Potential energy meaning stored energy. Just like if you raise an object from the Earth, you give it gravitational potential energy, the position of molecules relative to other molecules also gives it potential energy. So when you heat up some ice, the first thing that will probably happen is that the temperature won't change, it'll stay the same. As the ice starts to melt, what's happening is that the potential energy of the particles is increasing as they move further and further apart, as they start to slide around each other and increase the space between them. Then once it's completely melted, that's when the temperature will start to increase. The heat you're putting in is no longer going into potential energy, it's going into kinetic energy. The particles are moving faster. The same thing happens in all state changes. During the state change, the temperature stays constant because that energy you're putting in is not being changed into kinetic energy, it's instead being changed into potential energy, position-based energy. So if we plot a graph of temperature versus the heat we're adding to the ice, it will look something like this. Whenever there's a state change, ice to water, water to steam, or back the other way, the temperature remains constant. And in between those stages, the temperature can increase. So for example, the melted ice increases in temperature until it reaches the boiling point. And that's when the next state change can happen. So here we have the entire process from really, really cold ice increasing in temperature till it reaches the melting point, ice melting, and then the water increasing the temperature to the boiling point. Then the boiling process as the liquid water changes into steam. And then in theory, you could also increase the temperature of that steam. Although that last part is pretty hard to do. No matter how long I keep this pot boiling, it's never going to increase in temperature more. That's because the steam is escaping. The temperature of the water can only get to 100 degrees C, at which point it boils and turns into steam, and that steam escapes. If you could somehow contain that steam and heat it up more, then you could increase it above 100. I would have to somehow capture the steam to increase its temperature more. There are 2 equations that we can use to calculate how much heat we have to put in to do these things. For the diagonal parts of the graph, the parts where we're putting heat in and it's increasing the temperature of the material, we can use an MC delta T. Q is the heat added in joules to increase the temperature. And to calculate that, we take the mass of the substance, the amount of substance that we have, multiply it by C. That's called the specific heat capacity. It's a number that you would have to be given for the particular material. For example, water is 4187, ice is 2090. You could look that up in a data booklet or on the internet. And delta T is the change in temperature of the substance. That change in temperature can be measured in Celsius or Kelvin, definitely not in Fahrenheit. That won't work. The value of C, the specific heat capacity, changes depending on what the material is that you're heating or cooling. So for liquid water, it's 4187. For ice, it's 2090. If we were cooling the water instead of heating it, the graph would simply flip, but the amount of heat would still be the same. We'd use the same equations going the opposite way. But now Q would tell us how much heat energy we have to take out to decrease the temperature, as opposed to telling us how much energy we have to put in to increase the temperature. It's the same whether you're heating or cooling because energy is always conserved. So what about the flat parts? Well, for the flat parts we have a different equation. It looks like this. M here is the mass of the substance, but now we have a new constant H called the latent heat. And that can be either the latent heat of fusion, HF, or the latent heat of vaporization, HV. You use the latent heat of fusion when you're melting or freezing something, and you use the latent heat of vaporization when you're boiling or condensing something. Again, this equation will tell you either how much heat you have to put in to, for example, boil something, or how much heat you have to take out to condense it. That should be the same number whichever way you go. So water, for example, it has a latent heat of fusion of 3.35 times 10 to the 5, and a latent heat of vaporization of 2.26 times 10 to the 6. Now suppose we wanted to calculate how much heat it would take to change this ice all the way into steam. And let's say the temperature of this ice is really, really cold, like it's not even at the freezing point, it's well below, it's like negative 15 degrees Celsius. We would have to do a lot of heat calculations and add them up. We'd have to do an MC delta T for the ice increasing temperature from negative 15 all the way up to the melting point. Then we'd have to do an MH for the ice melting into liquid water. And then we'd have to do another MC delta T for the water increasing temperature up to the boiling point. And finally we'd have to do another MH for the water boiling into steam. And to find the total energy needed to do that whole process, we'd have to add up all the parts, all the Q's that we've calculated using each equation to get the total amount of energy, the total amount of heat energy we have to put in. And that will be measured in joules. One last thing, did you know that it's possible to skip all of these steps? A lump of ice can actually turn straight into steam with none of the in-between part. When a solid turns straight into a gas, that's called sublimation. And a gas can also turn straight into a solid, that's called deposition. But for that to happen to water, you'd have to decrease the pressure in the room, or maybe go up a mountain somewhere. However, we can see that process if we look at something called dry ice. Dry ice isn't water. Dry ice is solid carbon dioxide. That's one of the things that we breathe out. So it's normally a gas floating around in the air. But if we freeze it to form a solid carbon dioxide, we find that it sublimates straight into carbon dioxide gas with no liquid stage in between. And there's all kinds of fun things you can do with it. Let's take a look. Alright, so I have here some dry ice. It comes in a package full of all kinds of warnings about suffocation and cold burns and how you can hurt yourself. So this you can only sell to, depending on where you are, maybe you have to be 18 or 21. I'm going to take out the dry ice. I'm going to use a towel because I don't want to burn my skin. I don't want to produce a cold burn. This is not smoking because it's hot, it's smoking because it's really, really cold. So as you can see already, you can already see that there is a lot of vapor coming off this. So this solid carbon dioxide is sublimating into carbon dioxide gas. And that's just through the warmth of the room. It's being heated up by the room and that's causing it to change state into a gas. Okay, but we can accelerate this process. I have here some water. This water is significantly warmer than the dry ice. If I put it inside the water, the heat from the water will cause this to change state more quickly, and we should produce a more significant effect than this little bit of fog that you're seeing. Okay, so let's try that first. So I'm going to put it inside the water, and we're producing all this gas, all this carbon dioxide gas, like a fog machine. A few other things that we can do with it. You can take a rag and create a mix of water and soap. Try this bubble solution, I think this might work a little bit better. So I'll fill up the bubble solution. You can just use dish soap or something similar. So it's good and soaked. And in general, if you add lots of soap solution, lots of bubbles will be produced, and those bubbles are trapping carbon dioxide, so they're pure carbon dioxide bubbles. So another thing you can do is take a lump of dry ice and embed a coin inside it. You get some interesting effects. So let's see if we can do that. So I'm going to put it down on the desk, and then I'm going to just push the edge of the coin into the dry ice. And that's the effect. Pretty exciting. But this, not so much. Didn't anyone ever tell you that a watch part never increases in temperature?
Well, I obviously know that now.
Thanks for watching Flip Physics. Feel free to like this video and subscribe, but most of all, don't forget to leave a comment below with your questions, thoughts and suggestions. Until next time, keep questioning. And in the end, the heat you take is equal to the ice you make.